Hello, my IB physicists. Today we're going to be working on inertia stations, learning about Newton's first law of motion. It's page 4.7 and 4.8 in your IB physics binder, and it starts with this warm-up here. So you can actually go ahead and pause the video if you'd like. I'm going to read the questions, but pause the video and give these questions a little bit of thought. So, true or false? What is your thinking right now? So you could jot this down at the top of 4.7, and you're actually going to return back to this at the end of today's assignment. So is a force required to keep an object moving in a given direction? Is an upward force moving an object? An upward force moving an object must be experiencing, or at least usually does experience, an upward force. A rightward moving object must be experience, or usually does, a rightward force. A ball thrown up into the air and is moving upwards and rightwards towards its peak. So this is just like a ball that you throw to someone in an arc. The ball experiences a force that is directed upward and rightward. And if an object is at rest, then there are no forces acting upon the object. So now that you've done a little thinking about these, just jotted down your thinking right now, true or false, we're going to go ahead and move forward with today's assignment. So in today's assignment, you are going to be learning about something you probably have heard of before. I bet you can complete this sentence right here. An object at rest will stay, and an object in motion will stay, unless acted on by, yeah, you can complete this. So an object at rest will stay at rest, object in motion will stay in motion, unless acted on by an unbalanced force, or maybe unless acted on by an outside force, or unless acted on by a net force. Lots of ways we can finish the sentence. We're not going to watch this little sort of dopey old video, but this idea is called Newton's first law of motion, and it's the idea that if the forces are balanced, if you don't have an unbalanced force, if they are indeed balanced forces, that means that there is no acceleration. And this is often thought of as Newton's law of inertia, and it's something that is kind of challenging to understand. So the idea that an object will change its motion if you have an unbalanced force, easy to understand. If I put a force on my IB physics binder next to me, now it has tipped over onto the floor. Darn it, that was an unbalanced force. It caused it to have a change in its motion. That's pretty logical. But what's a little bit harder to understand is that when we have balanced forces, what that actually means is that there is no acceleration. It's not that there's no motion. It means that there's no acceleration. So if you have no net force acting on an object, it's said to be in translational equilibrium. And so this can actually take two forms, usually described thusly. So we can have balanced forces and a velocity of 0, where an object is sitting, staying at rest, pretty boring. Or we can have balanced forces with no acceleration, where the velocity is constant and non-zero. So that means that the object would be in motion and staying in motion. And so these two conditions of balanced forces will just continue being the condition of the motion of that object unless that object is acted on by an unbalanced force. And this is this big idea you've heard of before, but you maybe haven't fully understood before, of Newton's first law. And we call it the law of inertia sometimes. So you today are going to be exploring some stations. It's just a few stations that you're going to play around with. You might have done some of these before in middle school that you won't actually do today because I really cut down on how many stations you're looking at. You've maybe played with a tablecloth trick station. This is objects at rest, staying at rest. You've maybe played with little tricks with cards or other objects that you move suddenly and a thing falls into something, or toilet paper tubes. There's all sorts of little stations that you can play with inertia that you do really often in middle school that are usually about objects that are at rest, that are staying at rest. If you pull the tablecloth out quickly enough, the stuff on the table will stay at rest because there's not enough unbalanced force from the tablecloth on it to move it. But today's stations You're going to be looking at objects that are in motion for the most part, they're not entirely, and staying in motion, and really trying to get a feel for inertia with 4 different stations. So the first station is with PhET, and that's an online simulation that will go pretty quickly for you. And you're just playing around with forces and motion and this idea of friction, which you'll learn about a little bit more later this week. For each set of stations, you will be drawing some free body diagrams, thinking about what the different forces are on the objects. So that is station 1. It's on the internet. It tells you how to get there. I'll actually have a link here as well. Station number 2 asks you to toss a light ball and a heavy ball back and forth and compare them. And I would really recommend using like some ping pong ball maybe and an orange, or a ping pong ball and a baseball if you have it. If you don't have a ping pong ball, or like, I don't know, another similarly very light ball-like object, maybe a paper ball, you could make an origami paper ball if you want to do the most. You could also imagine what it's like to throw these objects back and forth. That would be okay. And for station number 2, you're just answering the first few questions. You don't have to try to play a game of broom ball. It's fine. We don't even have that. I don't even give you the directions for it, so don't do that. So you'll skip those 2 questions. Then station number 3, you're playing with a car and a passenger in the car, and I have 2 videos that are attached to this Schoology assignment that you can check out for that. And you're crashing that car essentially. So you want to be very safe while you're watching videos. I was very safe, and you should be cautious if you decide to try it at home with your own version of a tiny car. Station number 4 is playing with something called a hover puck, which is like a little, it's a toy, and it actually has little motors that cause air to jet out underneath the hover puck, causing it to hover on the ground, which is pretty cool. So I also have 2 videos attached to this assignment that you can check out for this hover puck that look at the hover puck in the 2 situations. The first situation with the hover puck on, and then the second situation is with the hover puck off. And so those are your stations. So definitely take a moment and pause this video, check out these stations, and then come back to this video. It's at 7:30, and I'm going to go over a couple other things on this last page of our inertia thinking. Okay, so the last page is going to help you really solidify this idea that an object with balanced forces on it means that there's no acceleration on the object. The object being at rest makes a lot of sense intuitively, but the object being in motion and having balanced forces on it, the forces add up to 0, is really kind of intuitively challenging. And so we're going to really hone in on that and hone in on this idea of inertia, which is the tendency of an object to keep doing what it's doing. So inertia is not exactly mass. It's proportional to mass, but what you've probably noticed is that objects that have more mass, like a heavier ball or the heavier PhET simulation objects, are harder, require more force to change their motion. So inertia is not mass itself, but it is proportional to mass, and it can really give us a sense of what is happening. So on the back page of, what is it, 4. I threw my binder to the floor, so now I don't know. Yeah, 4.8 in your binder. I have a spot for you to draw a velocity time graph and a force diagram, a free body diagram for these 3 different situations. Draw an object that is speeding up. Draw an object that is at a constant velocity, and an object that is slowing down. So take a moment and sketch in these velocity time graphs, and then think about what would the force diagram, the free body diagram, look like for those. And so what we notice is that if an object is speeding up, and these are all moving to the, left, yeah. If an object is speeding up, then the acceleration is in the same direction as the velocity. And that means that our unbalanced force is in the direction of the velocity. We have a larger applied force, or a larger push force, or normal force from whatever object is pushing this dog, I guess, to cause them to speed up. If we have our object at a constant velocity, so in this case our dog is being pushed at a constant velocity, notice there is still an applied force on the dog. That's because there's this frictional force on the dog between the surface that the dog is on. And so a constant velocity doesn't have no forces, it has balanced forces. And you also notice that the constant velocity doesn't have just one force moving it forwards. So we have balanced forces. And then if our object is slowing down, our acceleration is opposite the direction of the velocity. So that means that you've started pushing less than that amount of frictional force, or maybe not pushing at all. If we did not have an applied force here, the dog would be slowing down because of the frictional force, or maybe the hover puck would be slowing down because of the frictional force. Especially if the hover puck isn't on, then it has a lot of friction. So you want to jot in, if you haven't, these free body diagrams right here on your worksheet to really make sure you have a strong idea of the idea that the total force here is what matters. We're looking at the total, the net total force, telling us if those forces are balanced with our object moving at a constant velocity, or unbalanced, and that would be an object that is accelerating. Awesome. So if you needed to pause, hopefully you did. Pause right now if you need to, because I'm going to move forward to the bearded scientist, which is in fact the male, pale, and stale scientist. So people have been thinking about objects in motion for a long time. Long time. And the difficult thing about physics sometimes is that your intuition, our everyday experience with the world, doesn't lead to a super clear understanding of physics. So Aristotle originally claimed that in order to keep something moving at a constant velocity, you must push it with a constant force. And his reasoning was that if you push on an object, you make it move. If you stop pushing, the object stops, which sounds pretty familiar, right, with your everyday lived experience. But science, continued to move forward. People kept thinking about this, kept doing different experiments, either explicit experiments or just messing around and playing around with stuff to see what happened. And Galileo, a person you've maybe heard of before as well, said that a constant force causes the motion, the velocity of an object, to change. And a force is not required to keep the object in motion. His reasoning was that when an object slows down, that's because a force is acting on it. So that's a little bit more complete, a little bit closer to this idea of inertia you've been learning about today. And the understanding really got to be even more complete with this dude named Newton, who, in fact, these 3 laws we're going to learn about are named after. And his idea was that Aristotle wasn't quite right. That in fact, it's that when there's a zero net force, a zero total force acting on a body, that the body will either remain at rest or, that should be an or, continue to move along in a straight line with a constant speed. And his reasoning was that when you do nothing to an already moving object, it continues on with the same velocity. When you do nothing to an already still object, it stays still. And so this is this really much fuller idea of inertia and of what happens to objects. So take a moment and complete this last little bearded scientist section where you're going to explain what you know now about how to get an object to move faster, to move at a faster constant velocity. Because Aristotle was saying, if you want it to move at a constant velocity, you have to push it with a constant force. So I'd like you to explain what you'll have to do to get the object to move at a larger constant velocity than it was moving originally. Aristotle thought you just had to push it with a larger force to make it move at a larger constant velocity. But now that you've learned a little bit more about inertia, you know that that's not quite true. In fact, that's not true at all. So you want to describe that and then go ahead and take a picture and submit it to Schoology. And then finally, you can revisit these true or false questions and see how your thinking has changed. Thanks, guys.